That's okay.
Given that this is the last lecture.
Yes?
So last time I asked you about the issue that the Euclidean gravitational path integral pinches off.
Yes.
Therefore, there's
No trace.
Yeah. So that kind of kept me up that night. Is it possible to kind of artificially force the topology to be a cylinder, but allow, as a consequence, allow the metric to, when it reaches the sort of the horizon radius, allow the metric to have a degenerate direction. Instead of pinching off, kind of achieve the same geometry by,
In other words, you want to take polar coordinates, but not forget theta at r equals 0.
Yeah.
What you would say would be this.
And then eventually extend past that point.
Well, if you extend past it, then you get the second side. Well, okay.
Well, it depends on
Okay. Yeah,
the
okay.
integrating.
All right. Yeah, okay. You can try that. All kinds of things have been tried.
You can try that at your own peril.
Well,
So it's not a successful thing.
well, it's very hard to summarize in a couple of minutes, but yeah, we'd have to go on for a couple more months to give you a fuller picture about what's been tried and what is or isn't understood. But a quick statement is definitely that no one's gotten any substantial insight by anything like that. What's most likely to happen if you try is that you'll become more familiar with the difficulties, I think.
Is there a reference that you can recommend?
No. There's nothing that comes to mind. So on Tuesday, we derived the formula S equals A over 4G from the Euclidean action I interpreted as a multiple of the free energy and this nice formula. So it was a nice derivation, but as I presented it, which was the way Gibbons and Hawking did it originally, by the way, I sent a notification which had more details that we didn't have time for in class, and then I made a mistake, so I had to send it again. So if you look at that document, please be sure to look at the second version. Anyway, I presented it essentially as Gibbons and Hawking did originally. And it's a beautiful derivation that gives the right answer, but the answer proportional to the area seems to come out as a miracle in that derivation. So there wasn't any, you have to do a detailed calculation. And then in the end, you find that this expression is a multiple of the area. However, I want to now explain a variant that gives naturally that S is proportional to the area. And this is due, well, I'm not, well, if I had more time in this course, I'd explain a paper by Lefkowitz and Modesena. So what I'm going to be explaining is sort of a little bit of what's in Lefkowitz and Modesena, and that little bit sort of goes back to Susskind and Uglum. Anyway, there's a variant of the calculation that gives more naturally that the entropy is proportional to the area, and I want to explain that. So first of all, suppose there is some black hole mass we care about, and therefore we have beta Hawking is 8 pi gm. And suppose we somehow know what the action at beta equals beta Hawking for that particular value of the mass. Well, that doesn't determine the entropy. The entropy at that value of beta, because we need the derivative. But we only need a first derivative. So in other words, we let beta be beta h plus delta beta, and we work to first order in delta beta. So if we could calculate the action to first order in delta beta, that would be enough to find the entropy at beta h. Now, how are we supposed to find the action at beta plus delta beta, beta h plus delta beta, to first order? Well, one way is to repeat the calculation at the new value of beta. Well, that's essentially what we did on Tuesday. We did the calculation for any value of beta. But there's another way, which is as follows. So remember the black hole solution. And I'll write it in Euclidean signature. Well, so m is beta h over 8 pi g. So now, if you want to change beta h, you could change m in that formula. And if you do that, that changes the period of tau. Tau was a periodic variable with period beta. So we could follow the logic of Tuesday's lecture. To change beta h, we change m, and then we correspondingly change the period of tau. But that would lead back to method A. Then we could calculate the metric for the new black hole, and if we were going to do that, we might as well do the calculation we did on Tuesday. Instead, or we could change the period to tau order, tau going to tau plus beta h plus delta beta, without changing m. Well, what happens to us if we do that? We solve Einstein equations at away from the horizon, let's say, away from r equals 2 gm. But now there's a conical singularity. At r equals 2 gm. Because since we kept the mass fixed while changing beta, now the period is wrong to give a smooth metric. And instead, we have a conical metric. We have this, but we're trying to impose the wrong periodicity on theta. So it produces a conical singularity at the origin. Well, this isn't a solution of Einstein's equations, and beyond first order in delta beta, it would be the wrong thing to do. But to first order in delta beta, it's actually correct for the following reason. The two things, so we have two things. One is change beta and m to keep the solution smooth. Two is change beta but not m. Produces conical singularity. Now, these are the same. Up to a term of order delta beta. Because they both represent doing nothing from the original solution up to order delta beta. So they're both first-order deformations of the starting point. So they're first-order deformations of each other. If you look at the Lefkowitz-Maldacena paper, you'll see they discuss this point in detail. But I'm just going to say that two things that are infinitesimal departures from a starting point differ infinitesimally from each other. So now we use the fact that this one is a classical solution. And therefore, it's a stationary point of the action. Stationary point of the action means that the action doesn't change under a first-order deformation. And since 2 can be viewed as a first-order deformation of 1, it follows that the action is going to be the same whether we do 2 or 1. So 2 and 1 give the same action up to order delta beta squared, which we don't care about because we only need the delta beta term in the action so that we can compute the first derivative of the action at beta equals beta h. However, I want to explain more carefully the statement that the action is stationary under first-order deformations. So let's review the situation in classical mechanics. So here's one action, x dot squared, half x dot squared minus v. And now, consider a classical solution that starts at x1 at some time and ends at x2 at some other time, where x1 and x2 are fixed. And then we make a variation of x that is 0 at the endpoints. So the variation of the action is x dot delta x dot minus v prime of x times delta x. And then we want to integrate by parts and say that this vanishes by the classical equations, which quantum mechanically are also valid inside the path integral. But we get a surface term. So we get a term proportional to the equations of motion. Anyway, sorry. We're doing classical mechanics, forget path integrals. So we want to calculate the action of a classical solution with given boundary conditions. And the claim is that the action is invariant to first order under a small displacement. So that's called the principle of least action, so you're all familiar with it. But we're going to check it more carefully, including boundary terms. So I computed here the first order variation of the action. And then when we integrate by parts, we'll get a bulk term proportional to the equations of motion, minus x double dot minus v prime of x, which is 0 by the equation of motion. But we'll get a boundary term. And the boundary term for this action is delta x times x dot at the endpoints. So indeed, delta I is 0 if delta x is 0 at the endpoints. Now here's another action we could have used. We discussed it last time, actually. We could have used this action. So that action gives the same equations of motion. But it won't work here. This action is not stationary under variations that preserve the endpoints. Because when we compute the variation of the action now, we get, well, the important thing is that we get a bunch of stuff, but part of it is minus half x times delta x double dot. And then when we integrate by parts, we're going to get x times delta x dot at the endpoints. So this action will not be stationary under variations that keep the endpoints fixed. So in order for it to be true that the action is stationary under variations that keep the endpoint fixed, we need the same condition on the action that we imposed last time, which makes this one good and this one bad. So the action that has that property is not the naive action, but it's the Gibbons-Hawk-York corrected action. So in the derivation I'm giving you now, we're not going to subtract a contribution from R3 times S1. But we are going to include the Gibbons-Hawking-York term because we need to include it to make it true that the action is invariant to, if you have a classical solution, that the action is then invariant to first order under a deformation that preserves doesn't change the field at the endpoint. So we won't explicitly today have to invoke the Gibbons-Hawking-York term, but it's implicitly there because when we claim that the action is stationary, the version of the action for which that's true is the one that includes the Gibbons-Hawking-York term. So now we're going to go on to do a very quick calculation of the entropy using 2. So before I do that, let me just stop for a moment if there are any questions. Yes?
The claim that we have is that we're trying to make is that a small change in beta gives only a first order change in the action. So the change in the action is only first order in delta beta.
No, well, sorry. That's true even if you don't have a classical solution. If you change the field in order delta beta, the action changes generally by order delta beta.
Yeah, sorry, we want that term to vanish. We want it
Yes,
to vanish.
right.
But what we have is that it vanishes in first order in the metric. If you vary the metric, then the equations of motion mean that the first order change of the action vanishes. But it seems like by changing delta beta just a small amount, near the tip, you could have a very large change in the metric. So is that an issue?
Well, as I say, Meldesheim and Lefkowitz studied this more carefully. But in some sense, the change is large. It depends on your coordinate system. But it's proportional to delta beta. All that ultimately matters is that these two differ by something proportional to delta beta. I think it takes some thinking about it to become completely satisfied. And one algorithm is to look at the Lefkowitz-Meldesheim paper, but they're putting they put this calculation in a larger context, which I don't have time to explain. We would have explained it if we had a few more weeks in the course. I think it's best if I proceed with the calculation, and it might take some thought on your part to get completely satisfied with it. So now we're going to calculate the action using method 2. So 2 means that the metric is just the black hole metric where we keep m fixed. M is beta h over 8 pi g, which is constant. And we only change the period. So now let's calculate the action. Well, there's a bulk integral. There's a bulk integral at r bigger than 2gm. There's also a delta function. Well, I'll explain in a moment, but there's a delta function at r equals 2gm. But if I ignore the delta function, let's see, all that happens is that when we calculate the action, the metric is independent of tau, but we have to integrate tau from 0 up to beta. So therefore, we get a factor of beta, and that's the only beta dependence, since m is kept fixed. So the bulk integral is just going to be beta over beta h times whatever the action was at beta h.
So why, wouldn't the delta function also have delta beta?
We'll discuss the delta function in a bit.
Okay.
But let's discuss the bulk integral. Let's see. Naively, if you just look at this formula, if the metric was smooth, but tau had a variable period, we would say that just the integral is given, action is given by an integral proportional to beta. So it's, if beta equals beta h, it's whatever the action was at beta h, and in general, that's just multiplied by beta over beta h. But you see, this is annihilated by 1 minus beta d by d beta. So the slightly tricky calculation of the action is something we don't actually have to do in this approach. What we do have to do is to understand the conical singularity. So what I've drawn is meant to be what you get by taking a sheet of paper and folding it, cutting out a slice and then folding it into a cone. So it's flat away from the origin, but there's a conical singularity at the origin. And let's say that the angle let's say, well, I'll call it lambda. Let's say theta has period lambda. You know that if lambda is 2 pi, then that metric is flat. But in general, it has a scalar curvature, which is a delta function at origin times what? Times something times 2 pi minus lambda. I hope I have it written. Well, let me work out for you what it has to be. So, take a unit sphere. The scalar curvature of a unit sphere is 2. So the integral of the scalar curvature is the area times 2, which is 8 pi. Now, if you know your Gauss-Bonnet theorem, then you know that the integral of the scalar curvature is a topological invariant. So let me put another metric on the same thing. I'll take 2 squares and glue them together. So if I take two squares and glue them together, I've produced a metric on the sphere. I hope you understand what we do. We take the two squares, and we literally glue them together along the edges. This edge is glued here, this edge is glued here, this one's glued here, this one's glued here. That produces a metric that's completely flat except for 4 conical singularities at each of these points. And there's a missing angle, pi, at each corner. Because at a corner you have an angle pi over 2, you glue 2 of them together, you get pi. But a smooth point is surrounded by an angle 2 pi. So here we have 4 conical singularities, each with a missing angle pi. So scalar curvature at angle pi is 2 pi times the delta function. Since 4 of them have to give this topological invariant of 8 pi. So that tells us that the scalar curvature in general is 2 times the missing angle. If you're curious, you could do it with triangles instead of squares. I won't actually do it for you, but you could glue together 2 triangles. Well, I won't do it carefully, but just very briefly. If you glue together 2 triangles, you'd make a metric on the sphere that has 3 conical singularities. And from each one, the angle which is missing is, I think, 4 pi over 3. The angle is 2 pi over 3, so the missing part is 4 pi over 3. And then you have 3 of them. So you'll find that this formula still works if you glue together triangles. And if you're more ambitious, you can glue together n-gons for any n. So when you have a conical singularity, the scalar curvature has a delta function whose coefficient is 2 times the missing angle. Now here we have an angle which is 2 pi times 1 plus delta beta over beta h. In other words, we arranged so that the angle was 2 pi when delta beta was 0. And then if we shift delta beta, we get an angle which is this. So the missing part is actually minus 2 pi times delta beta over beta h. I want to try to get that right because I don't want to mess up the punchline unnecessarily. So, allowing for the 2 that we found in this calculation, it follows that the scalar curvature has a delta function at r equals 2 gm with a coefficient which is 2 times minus 2 pi times delta beta over beta h. So now we can calculate the action, and the only important part of the action comes from the delta function.
So don't you get a correction from the sphere?
From the what?
From the sphere?
Well, we'll integrate over the sphere. The delta function is supported on the sphere that lives at the tip of the cigar.
Yeah.
We're not.
Yeah, okay.
If we only had r and tau.
Okay, so the contribution like from
So-
involved then.
So, well, this is sort of a delta function in r and tau,
Yeah.
but it does nothing to the angles on the sphere.
Ah.
So when we evaluate the action, we're going to get, well, we had a term proportional to delta beta before. But the interesting part comes from this delta function inserted in the action. So it's minus 1 over 16 pi g. And now we can trivially do the integral The delta function does the integral over r and tau for us. And then we get a minus 4 pi times delta beta over beta h. And then we get the area of the sphere, which is the area of the horizon, because the sphere that lives at r equals 2 gm it's the Euclidean description of the horizon. So this is area over 4g times delta beta over beta h. And then we see that minus 1 minus beta, well, let me write delta beta as just beta minus beta h. Then we do 1 minus, sorry. Then the entropy then is 1 minus beta d beta of this expression, a over 4g times beta minus beta h over beta h. And that's just a over 4g. So this derivation makes it manifest that the entropy is a multiple of the horizon area. And it's universal. For example, it didn't have to be a Schwarzschild black hole. Nothing depended on the details of the metric. Okay. This derivation can be generalized a lot, but in particular it can be generalized for all kinds of black holes. It can be generalized beyond that. That's what you'll find in the Lefke Smoltosana paper. Any questions on this?
Does this derivation assume that we're in a thermal state? That we started with?
Well, it depends on what you mean. This derivation assumes this formula. And so you have to think back to how we motivated that formula. We motivated it by thinking of the black hole, Euclidean black hole, as a sort of instanton contribution to a thermal ensemble. So there's some underlying thermal reasoning when we decided that we would interpret this expression as the entropy. But once we decided that, we just are computing the action. We computed the action on Tuesday just directly from the definition, except we had to know about the Gibbons-Hawking-York term. And then we did it another way today, which had the advantage that it makes it obvious that why the answer is proportional to the area. Any other questions? Okay, if there are no more questions, we'll go on to the generalized second law. And we have about 50 minutes to explain the generalized second law, and I've never given this lecture before, so I have no idea if it fits in 50 minutes. And if it doesn't, I guess I'll have to write another note, like I've done after some of the other lectures. I hope that won't happen, though, because it would kind of spoil the punchline if we end today's lecture in the middle. So, what's the generalized second law? Well, Bekenstein said there was a generalized entropy. Which is supposed to be, well, I'll include Hawking's correct refinement with the factor of 1/4. So the generalized entropy is supposed to be given by this expression. And then, what is S out? Well, okay. The generalized second law, first of all, is supposed to say that the generalized entropy is non-decreasing. So our goal, to the extent we can achieve it in 50 minutes, is to explain how, well, a version of that statement that's true. So the first question is, what's S out? Now, to Bekenstein, S out was thermodynamic entropy. And if so, since thermodynamics isn't always valid, there's no hope for a truly universal statement that's valid under all conditions. And I believe for decades after Bekenstein's paper, most people did assume that there was no hope of a truly universal statement. But we've studied the von Neumann entropy in this class, and we learned that Cassini turned the Bekenstein bound into a universal statement, even though it had looked impossible. So we know what we're supposed to do. We interpret S out as von Neumann entropy. Of the region outside the horizon. Well, in general, to make a universal statement, we interpret entropy as the von Neumann entropy of a density matrix. But here, the logic of Bekenstein's thinking is that S out is the entropy outside the horizon, so it should be the von Neumann entropy of the density matrix. I'll call it rho or rho out, for the region outside the horizon. But there's an obvious, immediate issue, which is that then S out, interpreted as minus trace of rho log rho, is UV divergence. So it wasn't until 1993 that Susskind and Uglem, in the same paper I mentioned earlier as a partial precursor of the calculation we did that made it obvious that the entropy was a multiple of the area, they pointed out that A over 4G is also UV divergent in the following sense. When, in all our computations so far, G has presumably been the Baer-Newton's constant. So in all lectures until this point, we have never considered loops that renormalize the gravitational coupling. So G was really the Baer-Newton's constant, G0. But the relation between Newton's constant, the physical, but when Bekenstein said that the entropy was A over 4G plus S out, he presumably had in mind the physical Newton's constant, the one we measure in the lab. He wouldn't have been able to make any sense of what was the Baer-Newton constant. So we want to write the formula in terms of the physical Newton's constant, but all our derivations have ignored loops that renormalize gravity, so all our derivations in this course have involved the Baer-Newton constant. And the relationship between the two at one loop order is that 1 over G is 1 over G naught plus a constant times lambda squared. Lambda is a UV cutoff. So there really is a UV divergence in the relation in any attempt to physically interpret the results we've obtained in this course. Because all our results, although I've written G hundreds of times on the blackboard, since we were never taking into account loops that renormalized G, it was always a Baer classical G that entered all those formulas, including the ones until this minute in today's lecture. So Susskind and Uglem made the wonderful observation that although both S out and A over 4G have UV divergences, the sum is free of divergences. And therefore, the generalized entropy is better defined than either term is separately. And since we have to interpret S out as the von Neumann entropy in order to make that statement true, although Susskind and Uglum were not the first who interpreted, okay, you could argue that, okay, Susskind and Uglum were the first who showed clearly that S out has to be interpreted as von Neumann entropy. Let me put it that way. They were not the first who talked about von Neumann entropy in connection with black hole thermodynamics. As far as I know, that was Sorkin a decade earlier. Yes?
So comparing it to black holes now, in the formula above, we should now write a G0.
Well, if we write a G0, well, there are two versions of the formula. We could write a G0 and then a cutoff version of S out, or we could write a physical G and a renormalized version of S out. We're going to do a calculation which was basically done by Susskind and Uglum, and then it'll be clearer. So we're going to calculate, well, we're going to calculate S out. Well, or talk about calculating S out. We won't do a complete calculation, but we'll do enough of a calculation of S out to explain why the divergent part of S out is related to the renormalization of Newton's constant. So we assume a matter field. And if there is a matter field phi, it will do two things. One, it will contribute to the entropy, S out. And two, it will renormalize Newton's constant because there will be a loop. Oh, sorry. There will be a loop correcting the graviton propagator with phi inside. And that loop will be quadratically divergent. The entropy is also quadratically divergent. And Susskind and Uglum showed that the two divergences cancel in this formula. So S out is minus the trace of rho log rho, which, in the spirit of the replica trick, we interpret as minus d by dn of trace of rho to the n at n equals 1. We used that trick once before when we studied entropy for an interval in a two-dimensional conformal field theory. So, as I mentioned previously, most computations of entropy in quantum field theory use this formula. Although we haven't had time in this course to do very much with it. Now, so what is rho? Well, actually, so remember the black hole in Euclidean space is a semi-infinite cigar, which I'm drawing here, times S2. That's a topological description, not metrically. The metric on the S2 depends on how far out you are in the cigar. And if I take a cut from the tip of the cigar to infinity, that cut's supposed to represent a 3 manifold. So we take this semi-infinite line times S2. Okay. In this picture, okay, that's meant to be an initial value surface of the region outside the horizon. Now, it's problematical because it has an end. And it's because it has an end that there's a divergence when we try to talk about the entropy. This picture corresponds in the Euclidean picture to this one. So at the end of last lecture, we discussed a complete initial value surface that also includes the dotted line. And that corresponds to continuing the semi-infinite line around the backside. And then we did a path integral below. And that gave us the Hartle-Hawking state, which is the thermophile double state. So, rho out is just the trace over the left of psi Hartle-Hawking times psi Hartle-Hawking. In other words, we take psi Hartle-Hawking, which is the thermophile double state on the two-sided universe. But if we want a density matrix just on the right side, we integrate out the left side from the pure state density matrix, the projector onto psi Hartle-Hawking. Now, to do that by path integrals, we computed psi Hartle-Hawking by path integral on the bottom half of the cigar. That was the ket. So the corresponding bra we would compute by path integral on the top half. And then integrating out the left half means sewing together the part indicated with the dotted line. So to compute rho out, we do a path integral on the whole space just with a cut on the front side of the cigar. We do a path integral on the whole thing. Now, if you remember when we discussed Rindler space, we had the plane with a cut, a one-sided cut. We generated it by rotating a ray by a 2 pi angle around the cut. And then we said that the density matrix of Rindler space was e to the minus 2 pi k, where k is the rotation generator. Here we have the same basic idea. We have the semi-infinite cigar rather than the plane. It has a rotation symmetry around the endpoints. And we have a cut on a semi-infinite line that starts at that endpoint. And we could generate it by starting just below the cut and making a rotation by a 2 pi angle. So here rho is e to the minus 2 pi h, where h generates a rotation of the cigar. Well, h is viewed as an operator that acts just on states that live on a half line. And it, just like here, remember k was a one-sided, an operator that acts just on a state that lives on a half line and rotates it forward in Euclidean signature. So here, the density matrix is e to the minus 2 pi h. Now, why have I called the rotation generator h? I've called it h because at large distances from the black hole, this h is just the operator that moves us forward in imaginary time. So it's the standard Hamiltonian, up to a factor of beta Hawking, maybe. Sorry. If you normalize h as a standard rotation generator at the tip, so that it's correct that rho is e to the minus 2 pi times h rather than something else times h, then I think, okay. Anyway, h at infinity, well, the rotation generator is a multiple of d by d tau. But the period of tau was not 2 pi, it was beta h. So, okay. H is d by d theta, let's say, where theta has a 2 pi period. But beta had a period, sorry, tau had a period, which was beta h. So tau was beta h over 2 pi times theta. And in terms of tau, h is a multiple of d by d tau, but it's not 1 times d by d tau. So this formula corresponds exactly to a thermal density matrix at infinity. So this formula for the density matrix outside the horizon simply goes over at large distances to the statement that the Hartle-Hawking state is thermal at large distances. But it extends that statement into the region near the horizon, as we have to do if we're going to discuss what is S out. Any questions there? Yes?
So last lecture we saw that in order to get the entropy, like we needed to like cut like the space arm, right, the bounded part of like the black hole and the empty space on the side, and then we subtracted
Yes.
both. Right? And that was the thing that was like well defined. Is this process of subtraction any way related with the fact that you
We aren't going to have to compute a classical action today. In fact, what we're going to do, as you'll see, is more similar to the derivation I gave just 10 minutes ago. Except, well, there are differences, including the fact that we only will compute, well, here we're doing a quantum calculation, and we'll only discuss the divergent part. We won't say anything about S out except for its divergent part. And the divergent part lives near the tip here. So what happens at infinity won't be important. But at infinity, this is just a standard thermal ensemble. So the entropy is whatever you learned about in your quantum statistical mechanics. Any other question?
Why is it only at infinity that rho looks thermal?
Well, at infinity, see, rotating the cigar at infinity looks like a spatial translation. A spatial translation is a vector field that's covariantly generated by a vector field that's covariantly constant. A rotation isn't. The coefficients are not constant. A spatial translation is generated by a vector. Okay, d by d tau. Remember, tau is not a good coordinate near the origin. If you express d by d tau in terms of good coordinates near the origin, it would be something like this. It has non-constant coefficients. It generates a rotation of space with a fixed point. At infinity, not only is tau a good coordinate, but it's the Schwarzschild time coordinate. So at infinity, translation in tau is generated by the ordinary Hamiltonian.
So tau is not Schwarzschild time everywhere. I thought tau was.
You could claim it's Schwarzschild time everywhere, but near the horizon, Schwarzschild time isn't a good coordinate.
Okay. So everywhere away from the bifurcation surface, rho is.
Well, many people would say that. I don't like it, as I said in a different context the other day, because a thermal ensemble only makes sense if the temperature is almost constant over distance long compared to 1 over the temperature. That condition is satisfied near infinity, but it's not satisfied when you get close to the black hole. Okay. Now that we know that rho is e to the minus 2 pi h, we can then say that rho to the n is e to the minus 2 pi n times h. And now how would we calculate the trace of rho to the n? Well, we just take the initial value surface and we rotate it but we rotate it by the wrong angle. Two pi n. If n is 1, we rotate by the angle 2 pi and we build up the Euclidean black hole. But if n isn't 1, we rotate by 2 pi n and we build up a conical singularity. So, to calculate trace rho to the n, we have to do a path integral for our matter field on precisely the space-time that we used in the first part of today's lecture, which was a black hole where we took the wrong period for tau, so that the angle was not 2 pi now, but 2 pi n. Previously, in the last explanation, it was 2 pi times 1 plus delta beta over beta h. And now we have the same thing with delta beta, with 1 plus delta beta over beta h replaced by n. But we have exactly the same space-time. A difference is that now we're not computing the classical action. We want the we want the path integral of the phi field. So, to get the contribution of phi, the contribution of a matter field to S out is its contribution to minus d by dn at n equals 1 of trace rho to the n. And trace rho to the n is just the phi path integral with the conical singularity. So we're expecting to get an ultraviolet divergence because we know from previous discussions we expect the entropy to be ultraviolet divergent. And the ultraviolet divergence has to come from the divergence of the path integral of phi in the presence of the conical singularity. Well, on any space-time, the phi path integral is divergent. And we're going to get divergences, for example, that will be lambda to the fourth times the volume of space-time. That renormalizes the cosmological constant. If we're discussing quantum gravity in an asymptotically flat space-time, then we've picked the renormalization scheme where the renormalized cosmological constant is 0, so we don't have to care about that one too much. Then here's another term that could be present in the action. We could get a quadratically divergent term that's proportional to the bare Einstein-Hilbert action. Well, if such a term is present, it will renormalize Newton's constant. And as I told you, Susskind and Uglum argued that the renormalization of Newton's constant exactly cancels the divergence in S out. So what we're interested in is precisely the fact that there can be a term in S out that's divergent and is related to the renormalization of Newton's constant. So that will be this term. So you see that the phi path integral on the space-time with the conical singularity, or I call it just the conical space-time, has a divergent contribution that lives at the horizon. We have an angle n at the horizon, or sorry, 2 pi times n. So you see, we have an excess angle, 2 pi times n minus 1. So the scalar curvature has a delta function it has a smooth stuff, but what we care about now is that there's a delta function at the horizon times 4 pi times n minus 1. Sorry, with the minus sign. Remember that we computed that the scalar curvature has a delta function which is minus twice the excess angle. So here the excess angle is 2 pi times n minus 1, so the delta function is minus 4 pi times n minus 1. So the phi path integral has a divergent piece. This is the phi path integral on the conical space-time. It has a divergent piece, which is c lambda squared times whatever we get when we evaluate this thing on the conical space-time, and the delta function contributes minus 4 pi times n minus 1. Then S out is minus d by dn at n equals 1 of trace rho to the n. And trace rho to the n have this contribution. Times the area. Well, just as before, when we evaluate the integral d4x of the square root of g times r, we get a delta function in 2 coordinates, and then we get the area by integrating over the other 2 coordinates. So the divergent contribution to the phi path integral in the conical manifold looks like this. And then if we calculate the n derivative at n equals 1 with the minus sign, we get c lambda squared times 4 pi times the area. So we learned that S out is c lambda squared times 4 pi times the area plus something finite, which would be the renormalized. You could call the finite thing the renormalized S out. So now, therefore, the generalized entropy is A over 4G naught plus S out. It's equal to A over 4G naught plus 4 pi. Oh, sorry. What did I do? Okay. So the generalized entropy is the renormalized area times something. And I claim that this expression here is just 1 over G. Because we have the bare gravitational action and then we added to it this piece that came from phi, and we interpret that as the renormalized gravitational action. So you see, 1 over G is 1 over G naught plus 16 pi C. Sorry, thank you. So that's what Susskind and Uglum said in 1993. And as you can see, it was a well, quite lovely and actually, in hindsight, rather simple argument. It's got one drawback, which has never been completely fixed. This argument was valid for every matter field except the gravitational field. Or in supergravity, you might have trouble with the gravitino. So I don't think there's an equally clear explanation that this is true for the renormalization of Newton's constant due to graviton loops. As stated, it works for loops of all other fields. I'm sure in one loop order you could justify this for a graviton loop, but okay. Conceptually, I explained this in terms of a matter path integral in a conical spacetime, and that framework isn't quite adequate with gravity for the gravitational loops themselves. So there's a bit of a gap in this understanding, but I don't think it's better understood than what I've told you. Any questions? Okay.
So how come this C cannot be the same now that for the two different paths?
It's the same path integral.
Well, one we did over there.
Oh, one we did in any spacetime. So in any spacetime, there's this kind of divergent contribution.
Yeah, for sure, but now we all set with the
Now we
C.
specialize it. Now we specialize it to the conical spacetime of interest. But we use the same formula because it's a universal formula for any spacetime.
But not with the same C, right?
No, the same C. C is universal.
C universal.
Yes. A universal, in general, ultraviolet divergences are always given by universal local expressions.
Yeah, okay.
So there's a formula like this with the universal C, independent of the spacetime. It's only because it's universal that the divergence can be absorbed as a renormalization of Newton's constant. And then all we did was to take the universal formula and implement it in the conical spacetime. Any other questions?
So is this correct that this C encapsulates all orders in all loops?
Well, this calculation, as stated, would be valid for all loops as long as the fields inside the loops are not gravitons themselves. And as I've said, I don't think that an improvement is really well understood that includes the gravitons inside the loops. Okay. So now we've learned that the S out has to be the renormalized von Neumann entropy, and we've also learned, that the statement potentially makes sense because S generalized entropy, has no UV divergences and is therefore well defined. So it's conceivable that the S gen dt is always true. It's not just conceivable, but it was actually proved by Aaron Wall in 2012. I wanted to do a reality check first, though. Trouble is, okay, I could skip it and come closer to finishing the lecture, but I hate to do that. So we look at a black hole radiating into empty space. So its mass is going down, and therefore its area is going down. And therefore, the area term in the generalized entropy is going down, but S out is going up. So we'd like to know that S out goes up by more than A over 4G goes down. Now, I'm going to consider a shell of radiation emitted in a certain time, delta tau. So what is going out we'll think of as n 1 plus 1 dimensional partial waves. Where n, to compute n, we need to take into account the gray body factors. So when we discussed Hawking radiation 2 Tuesdays ago, we first considered a wave that propagates to infinity with no obstruction. Then we understood that in general there's a potential barrier and there is an obstruction. The potential barrier is very strong for high angular momentum. It's weaker for low angular momentum. So some waves get out, some waves don't get out very much, and some waves partially get out. When all is said and done, there's an effective number of partial waves that are getting out. So I'll call that number n. It's not really an integer. To compute it carefully, we need to use the gray body factors. But to give you the basic idea, assume that there are n partial waves that go out unobstructed, so we can use free field theory to compute their thermodynamics, and that all other waves are completely obstructed by the gray body factors. In other words, I'll assume the gray body factors are 1 for some values of angular momentum and 0 for others. N is the number of factors where they're 1. Then I'll also assume that modes are all bosons for simplicity. Then we have the thermodynamics of a 1 plus 1 dimensional massless free field. And in that thermodynamics, the energy is pi n times the temperature squared over 12 times the length. And the length is going to be c tau, because we look at, or c delta tau. The modes are going out at the speed of light for a time delta tau in this interval. And 1 plus 1 dimensional thermodynamics also tells us that S is pi n over 6 times t squared times the same thing, L. Now, what's important is going to be the ratio of those two. And the ratio just comes from dE equals TdS. So, well, if you define n to make this formula true for S, it's not t squared, it's t. You know that the entropy density is proportional to the temperature. And what I'm going to say, the coefficient isn't very important, but it actually is pi over 6 times the number of effective modes times the length. Whatever the coefficient is here, the coefficient of the energy is half as big, 1/12 instead of 1/6, in order to satisfy dE equals TdS, because the energy is proportional to the temperature squared, while the entropy is proportional to the temperature. So, when the black hole radiates, the change in the energy of the radiation is T Hawking over 2 times the change in the entropy of the radiation. The temperature is T Hawking, and the 1/2 is just the 1/2 I just explained that's needed to satisfy dE equals TdS. Now, by conservation of energy, the energy change of the black hole is minus the energy change of the radiation. The black hole evolves adiabatically. So dE of the black hole is T Hawking times ds of the black hole. And I look at a shell that's small enough so that T Hawking can be treated as constant. So therefore, delta E of the black hole is T Hawking times delta S of the black hole. So from that I learned that delta S of the black hole is delta E of the black hole over T Hawking. But that's the same as minus delta E of the radiation over T Hawking. But this formula tells me that delta S of the radiation is 2 over T Hawking times delta E of the radiation. So when the black hole entropy, when the area term when the entropy of the black hole goes down by a certain amount, the entropy of the radiation goes up by twice that amount. So this is an example of the generalized second law at work. Now, why did it happen? Well, you see, thermodynamics would have predicted it. The black hole is a hot body with a temperature T Hawking. We assumed it was radiating into empty space, so it was radiating into the vacuum at temperature 0. So we brought an object of temperature TH into contact with a body of temperature 0, so naturally the entropy went up. And, well, if you think through more carefully this derivation, you'll see that the only facts we used are the same facts that would be used in general to show that the entropy increases when two bodies of different temperature are in contact with each other. So what's going on? The entropy increased because radiation of a black hole into empty space is thermodynamically irreversible because empty space has 0 temperature. If we took the temperature of, if we had the black hole radiating into a universe that was just infinitesimally less hot than the black hole, we could make the black hole radiate reversibly without changing the entropy. But a black hole radiating into empty space increases the entropy. Yes?
I want to slow you down, but it is obvious that your definition of entropy on the last blackboard is the same one as the Neumann entropy.
Well, it is obvious because if you have ordinary matter far away, well, when von Neumann entropy is well defined, when von Neumann entropy is well defined and thermodynamics is valid, von Neumann entropy agrees with thermodynamic entropy, because textbooks show that thermodynamic entropy is minus trace of rho log rho.
Because they agree. If in the end the information is coming out of the black hole.
Okay. Herman's asking a question that belongs in the analytic continuation of this course into the second year. So I'm not going to comment right now, if you don't mind. Excuse me.
Is there going to be a continuation of the second year?
I'm not planning it right now. Okay. Now, let's remember that in general, if we have a region of space-time V and a larger region U, then, and we have two density matrices with density matrices rho and sigma for the different regions, then the relative entropy in the smaller region is equal to or less than the relative entropy in the larger region. We used this once in this, well, we proved this a few weeks ago, but we used it once when we were discussing the ANAC. The ANAC in Minkowski space was the only application we've given until now of this fundamental property. When we discussed the Bekenstein bound, we used the more elementary fact, much more elementary, that the relative entropy is non-negative. But after Cassini had shown that the Bekenstein bound corresponds to non-negativity of the relative entropy, Wall showed that the much deeper statement of the generalized second law comes from monotonicity of relative entropy. And that's what I'd love to explain, but unfortunately we have 3 minutes. I really wish no other class was coming. Then I would just finish, we go on and explain it to whoever wants to stay. But I think we're going to have another class coming. So we'll do whatever we can, but. So, first of all, the proof is an expansion in powers of h bar around the classical case. So, if we include powers of h bar, then the area term is of order 1 over h bar, and S out is of order h bar to the 0. So the leading term is the area term. And if the area is increasing classically, then the generalized second law is trivial. So the only interesting case is the case that classically the area is not increasing. So we should begin by investigating that. And for this, we need the Raychaudhuri equation. It's really a shame to run out of time in this derivation because the proof of the generalized second law really ties together everything we did in the course. So remember that the horizon is a null surface. So the metric of the horizon is of codimension 1. So it has coordinates xa, where a runs from 1 to d minus 2. And one more coordinate, light cone light coordinate. I'll call it V. So a total of d minus 1 coordinates. The horizon, we learned earlier that the metric of a general horizon takes a special form because the one coordinate is null. This is meant to be 0 times dx dv and also 0 times dv squared. And then we let the area density be the square root of the determinant of G, and we define theta to be A inverse dVA. And then we had Ricciardori's equation. Ricciardori's equation said that d theta dv is minus theta squared over d minus 2 minus sigma AB minus 8 pi g tvv. And we use this equation to prove the area theorem, which said that d theta dv is equal to or greater than 0 everywhere on the horizon. Now, since theta is the area increase, whenever theta is non-zero, the generalized second law is trivial. So we only need to study the generalized second law we want to study it when theta is 0. But it's very, when theta is 0 and therefore dv theta is 0. So to make that true, we see that you need sigma AB to be 0 and also tvv, the stress tensor, has to be 0. Now sigma AB being 0, well, sigma AB was the traceless part of G inverse dVg. Maybe with a 1/2, I think. So theta equals sigma equals 0 means that the metric is actually independent of V. So the case where the generalized second law is interesting is the case where, first of all, the horizon is stationary. And second, the classical stress tensor coming in across the horizon is 0. There will be a quantum stress tensor due to loops, but the classical one is 0. As an example of the loops, we could consider a Schwarzschild black hole radiating into empty space, as we discussed before. We didn't compute the expectation value of the quantum stress tensor, but Hawking radiation is related to the fact that there is a negative expectation value which causes the black hole mass to go down. We didn't compute it because that's a harder way to understand black hole radiation than the things we actually did do. But in the generalized second law, you're interested in the quantum correction to TVV and also the quantum contribution to S out. Now, in order h bar, well, TVV is non-zero, but sigma AB is of order h bar squared. Well, I'm cheating slightly because there's a graviton contribution that's of order h bar. The same remark I made before applies, that the gravitational contribution is less well understood. The contribution due to gravitons is less well understood than the contribution of other matter fields. You can argue that the order h bar term in sigma squared comes only from gravitons and is similar to the matter contribution to TVV. But we won't discuss that. So the generalized second law we want to look at the h bar contribution in S out, the h bar to the 1 contribution in H out, which I'll just call AH bar. And we want to look at the h bar to the 0 contribution. Sorry. We look at S out in order h bar to the 0, and we look at the order h bar correction to the area because there's an explicit 1 over h bar here. So what we're going to prove, assuming that another class doesn't come in and stop us from proving it, is that the order h bar contribution to the area plus the order h bar 0 contribution to the S out are such that S gen is increasing. Now we might as well now compute the order h bar contribution to the area. So we'll do it from Ricciardori's equation, which I hope I haven't erased. We don't need to consider this because it's of order h sigma squared. Likewise, this is of order sigma squared. So we just have d theta dv equals minus 8 pi, well, d theta dv in order h bar is minus h pi g times the contribution of order h bar to the matter stress tensor. We've assumed the contribution of order h bar to the 0 is 0. That's a little ominous, somebody opening the door. Is there a room next door we can go to, Herman? Can you check if this room by miracle is free? Okay. 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 So we have in detail d by dv of 1 over a and h bar to the 0 times dv of a h bar is minus 8 pi g times tvv h bar. And the unperturbed A is area density is independent of V. That's what made the generalized second law non-trivial. So we get that d squared dv squared of the order h bar correction to the area density is minus 8 pi g times the area density itself times tvv in order h bar. And you can solve this equation. So the solution isn't unique because it's a second order equation. But I'll write a solution which is the only physically sensible one. The other solutions have an unphysical behavior for v going to infinity. Although I don't have time to discuss that carefully. The solution that's physically relevant is we want to evaluate the correction at some value of v, which might depend on x. Remember, Ricciardori's equation is at fixed x as a function of v. So we want to evaluate at some value of v, which depends on x. And the solution of this equation gives us that AH bar is an integral from v equals f to infinity, dv prime, of v prime minus f times the expectation value of tvv in order h bar. So what I've done is to find a solution of that equation. You can check it solves the equation, and it doesn't have the bad behavior at v equals infinity that other solutions have. So I apologize to those who have to leave for running over. You will find a summary of this in a document I sent to some of you in one of the notifications. Okay, so let's put this formula for AH bar on the shelf for a little bit, because now we have to learn something about the entropy. So we'll draw a more realistic picture of a black hole that may be formed from collapse. So we think of this as a general black hole that somehow formed in the universe. And then we consider two cuts of the horizon. Let's say at U and V. U is V equals f of x, and V is little v equals g of x. And then we want to measure S out here or here. So the region outside the horizon at one horizon cut is here, and the other region outside is the other horizon cut is here. And the generalized second law says that the area at V over over 4G h bar plus S out at V is supposed to be equal to or bigger than the area at U over 4G h bar plus S out of U. Now, it might not be immediately obvious that we can use monotonicity of relative entropy here. The reason we can is that a knowledge of the quantum fields on U determines them throughout the domain of dependence of U, which is this region. A knowledge of the quantum fields on V determines them in the domain of dependence of V, which is a strictly smaller region. Is there any solution, Herman? You moved the other class? Okay. So again, I apologize to those of you who have to leave. This is going to go on for another 10 or 15 minutes, probably. So see, the generalized second law says that if you take measuring the entropy at a given time means for a given horizon cut. And then you measure the generalized entropy outside, the von Neumann entropy outside plus the area of that cut. That's the generalized entropy. The generalized second law says that that increases as you go toward a future cut. Going toward a future cut means that the associated space-time region is smaller. The associated space-time region is the domain of dependence of the cut. So since we have a region and a smaller region, we have monotonicity of relative entropy. So for any two states, rho and sigma, the relative entropy on the later cut my phone is telling me that I'm one of the people who have to do something else, but okay. Monotonicity of relative entropy tells us that the relative entropy on the later cut is less because the later cut corresponds to a smaller region of spacetime. Now, as in the proof of the Bekenstein bound, we expand the relative entropy. It's trace rho log rho minus the trace of rho log sigma. So it's minus S of rho minus what I call E of rho. I called it, in my notes I called it plus E, where E is minus trace of rho log sigma. So using that, we see that, sorry, this is minus S of rho plus E of rho. We get that minus S of rho v plus E of rho v is equal to less than minus S of rho u plus E of rho u. Or in other words, S of rho v minus E of rho v is equal to or bigger than S of rho u minus E of rho u. This is what we got directly from monotonicity of relative entropy. Now, let's compare that to the generalized second law. The generalized second law says that S of rho v plus AV over 4G is equal to or greater than S of rho u plus AU over 4G. So we're almost there. If I compare what we know to what we have, you see what we need is well, we could here replace the areas by their parts of order h bar. Because we're interested in a situation where the classical terms were equal, so it's only the order h bar terms that matter. So what we need is that the area of V of h bar over 4G h bar should equal to, well, we need to somehow turn this into this. It has to be equal to what we call minus, I called it EV or something. Or E of rho V, I called it. So we needed that to be true for V and similarly for U. We want that to be true for any cut of the horizon, since the generalized second law is supposed to be true for any pair of cuts. But we've got a handy formula that we already computed. Okay, well, we computed it for the area density. So the area is just the integral of the area density over the horizon. So the area in order h bar is minus 8 pi g times the integral for, this is the area in the horizon for the cut V equals F, is gotten by integrating this over the horizon. So it's minus 8 pi g times the integral from V equals F to infinity, dV prime, V prime minus V, times the expectation value of TVV. And by definition of the density matrix, I can write the expectation value of VVV in terms of the trace, just as a tautology. Let's write it in terms of the density matrix. Sorry, I think this is V prime minus F. We can call this the trace of rho V times TVV, the order h bar part. I'm just saying that the expectation value, rho is the state in which we're trying to prove the generalized second law. So the expectation value of TVV in that state is by definition the trace of the density matrix times TVV. Now I haven't told you what sigma is, but when I replaced S of rho, when I said that S of rho was S out, to make that true, rho was the state in which we're trying to prove the generalized second law. We haven't decided what sigma is. And E of rho v is minus the trace of rho v log sigma v. So, well, the left-hand side, this thing, has this formula. And the right-hand side, this thing has this formula. I think with the plus sign because there was a minus sign in the definition of E. So to make the two formulas the same, what we need is So allowing for the 1 over 4g in one formula and the 8 pi g in the other formula, which has the relative 2 pi, and also allowing for the minus sign in one formula. What we need to make it all work is that the logarithm of sigma v should be minus 2 pi times the integral for v equal to bigger than f. I'm afraid, contrary to what I said here, I'm taking capital V to be the region defined by f. In most of the formulas, I've done that. So I've never until now said what sigma v is. But now we discover that if there is a density matrix such that this is true, then monotonicity of relative entropy for that density matrix is the generalized second law. Now, if I haven't worn you all out too much, you might recognize in a moment that we know what's the state that has this density matrix. It's the same, we used the same formula when we were proving the ANAC. So we're going to look at an auxiliary spacetime with 1 plus 1 dimensional Lorentz invariance. The auxiliary spacetime will be 2-dimensional Minkowski space times the horizon we're actually interested in, which will give this metric that it actually has. So in other words, we embed the horizon we're actually interested in an auxiliary spacetime with this metric. So we study whatever matter quantum field theory we've got in this spacetime, and then it has a vacuum state omega. And then we look at the cut at v equal to f of x. I'm drawing it in one dimension. X is our coordinates on additional dimensions that aren't drawn. But so we embed the horizon at u equals 0. So the horizon is then parameterized by x and v. And since there's no dv squared or dv dx in this metric at u equals 0, v is a null coordinate. And I've simply embedded the horizon we're interested in some other spacetime. Then we take the vacuum state of whatever quantum field theory we're studying, but in that spacetime, and we let sigma f be the trace over the region where v is less than f of x of the pure state density matrix of the vacuum. So sigma f is the density matrix of the vacuum for the region where v is bigger than f of x. Now, if I haven't tired you all out too much, you might remember that when we were doing the proof of the ANAC, we were in Minkowski space, so the transverse metric was flat, but that wasn't important in the derivation, actually. And then we considered the density matrix of a region where v is bigger than some cut f of x. And we deduced that the logarithm of the density matrix was precisely this. So the density matrix of the vacuum in this auxiliary spacetime, reduced to the region above the cut, is precisely the density matrix that we need to complete the argument of the generalized second law. Now, I've swept under the rug many details that you can find explained more thoroughly in Aaron Wall's paper. But there's only one thing I want to mention. We could be studying a black hole that formed from collapse. And then the horizon settles down classically to a stationary state where we're making this argument. And if so, the past part of the horizon didn't exist in the physical spacetime. But it existed in the auxiliary spacetime that we used in the argument. That's actually not a problem because we only were interested in a possible density matrix of the quantum fields in the region that does exist in our spacetime the region that does exist was part of the auxiliary spacetime. So if you take the vacuum in the auxiliary spacetime and then construct the reduced density matrix above the cut, that makes sense as a density matrix in the problem that we're actually interested in. And that's the density matrix that makes the argument work. Now, I want to thank you for your patience in staying till the end, and I want to apologize to those who aren't here, although they're not here to hear the apology. I might send it in a notification. And if I zoom through this a little bit too fast, at least there's a short written version in the set of slides in one of the notifications. So I guess I'm supposed to stop here for any quick questions, although I understand everybody wanting to rush out since you probably are all busy with other things. But if anyone wants to stay and ask another question or two, go ahead. Okay. Well, if you want to hear one more lecture by me, you can come to the PTCS at 9 a.m. on Monday. That's part of this program that's going on next week at the PCTS. And it'll be in the spirit of the things we could have discussed in this course, but because most of the audience will have missed the course, it'll be presented without assuming that they did hear the course. Okay.